Hello everyone, I'm Boyuan Wang. I'm an undergraduate student in Central University of Finance and Economics, China. Our paper's title is Graph Transformer, Learning Better Representations for Graph Neural Network. Graph is a widely used data structure to model complex objects and relationships, such as compound and social network. Therefore, there is a high demand for graph classification. The major deep learning approach now is to use graph convolutional network, or GCN. There are two main categories of GCNs, that is spectral and spatial. But spectral method cannot be expanded to big graphs well. By contrast, spatial approaches are more flexible. However, there are two major issues existing in spatial GCN. The first one is oversmoothing. Oversmoothing is a phenomenon that, as the network layer goes deeper, each vertex features appears to be similar and loses its distinct information. The second problem is that distant substructures of a graph may be correlated and provide latent information. However, major spatial methods now either learn these links too late to be oversmoothed or just ignore these distant links. Our approach aims to solve this problem by learning these relations timely. There are three important related works of our model: Subgraph Convolution Network, SCN, Deep Graph Convolutional Neural Network, DGCN, and the idea of transformer. Detailed procedures of SCN and DGCN are shown in the slide. SCN let regular convolution perform on m-array k-depth subtrees of each vertex, and the DGCN provides a pooling method named sort pool for graph classification. Transformer achieves great success in NLP tasks. Its key idea is multi-head attention that can learn remote tokens connections well. We combine the features of these works and proposed our model. Our model is called the Graph Transformer with Mixed Network, GTMN. At each step, the proposed Graph Transformer unit, GT, takes in the input calculated by SCN and the previous output. Each GT calculates the latent relationships between substructures with different sizes. Up to k steps of GT are performed. Output then is fed into a set of GCN layers. There are n GCN layers in total. For n GCN layers, output at layer I is concatenated, and then n plus 1 big feature matrices are formed. Furthermore, all of them are concatenated and fed into layered sort pool. The final part of the network is to transmute graph features into grid structures and make a prediction for the input graph. Specifically, we propose Graph Transformer unit. This unit can learn latent relations well, as it can capture meaningful potential relations and learn better representations of multiple scales. Concretely, the equation below makes GT learn a better graph representation through a learnable relation matrix and aggregate these latent relations. Thus, each head can learn a distinct latent relation, and the multi-head attention layer is able to learn multiple latent relations. With these better learned representations on hand, GCNs can solve the problem mentioned above better. Our proposed GTMN has a number of advantages. First, GTMN can get better graph representations with the help of GT units. This alleviates the problem of oversmoothing, because only few convolution operations need to be performed in the GCN step. Second, we combine SCN with DGCN through the proposed GT units. More generally, each two methods of graph approaches can be mingled by the proposed GT. This helps the network to take advantage of the two underlying methods and relieve their individual drawbacks. Concretely, the method that GT takes in just plays subsidiary role to learn better local information. The other method that GT outputs to is the main model to learn the representations learned by GT. In conclusion, GTMN can learn both local and global information with any two methods combined. GTMN is able to well extract latent relations between substructures and output better graph representations. We evaluate the performance of the proposed GTMN model and compare it with the state-of-the-art methods, including traditional and deep learning approaches. The benchmarks are abstracted from bioinformatics and social networks. Our model outperforms most of the approaches and demonstrates its effectiveness. In conclusion, first, we illustrate the problem why distant relations cannot be well learned and propose a novel graph transformer unit, GT, to learn latent relations between substructures at arbitrary locations. Second, we develop a mixed neural network that innovatively combines random walk with graph convolution methods. For example, SCN with DGCN. Third, we empirically evaluate the performance of the proposed GTMN on graph classification benchmarks. Experimental results show that when compared to other state-of-the-art methods, our approach is effective. After all, our approach still exists many to study. First of all, graph transformer units can be used in more tasks, and thus further experiments need to be performed. Also, due to the limit of time and page, our paper does not mention or figure out what GT really learned. Hence, we further need to perform ablation study and get a reasonable conclusion. And that's all. Thank you for listening.